Hello, AP Stat students. Today we will finish up Chapter 11 by doing 11.2b notes. We are going to talk about the chi-square test for association or independence. When sampling from a single population, we can analyze the relationship between the variables to see if there's an association, meaning it's dependent, or no association, independent, because remember, independent means they don't affect each other. So this particular test uses one population or one random sample, but two variables. Here's what the test would look like. So in the state portion, we want to perform a chi-square test of association at whatever significance level. For the null hypothesis, it is worded in such a way that you would say there is no association between whatever the two variables are. And the alternative, there is an association there, that there would be a relationship between the variables. Then you check the conditions. They're the same conditions as the chi-square test for homogeneity. To do the large sample, you take those marginal distributions and multiply it by the total for each category. And then independent conditions the same. The chi-squared statistic is also the same. It's observed minus expected quantity squared divided by the expected. List out the first two terms, calculate the p-value. So you're going to do the chi-squared CDF. And the degrees of freedom still the same. It's the number of categories minus one of a row, and then the times the number of categories minus one in the column. And the p-value is the probability of getting the chi-squared statistic if the null is true. I'm not going to fill out the rest of it because we've done it over and over again that you should know it. So I'm not going to go over the conclude. But then for the follow-up, which cells show the largest deviations, which direction are the deviations? And remember, the key thing to note here is that association does not mean causation, especially if you're um, getting a random sample. Now, if you're getting a random assignment, you can establish causation because you're doing an experiment, but not for our simple random samples that we're doing. And so you could state your alternative hypothesis or your null and alternative using the words no association and is an association, which most students like to use, or you could choose to do it this way. We want to perform a chi-square test of independence at the whatever significance level. In the null hypothesis, you would say that the whatever the variables are independent. So independent, and this just throws students off, means they don't affect each other. Because one has no effect on the other. And so the alternative hypothesis is that they are not independent, meaning they do have an effect of each other, effect on each other. So it's the same as there is an association. And so it just throws students off because in the previous one with the um, association, you clearly state no association in the null, and there is an association in the alternative, and you just switch that around if you're going to use words like independent, not independent, and everything else is the same. So we don't need to go over that. Okay, let's do an example. In an example from chapter 5, we investigated the relationship between gender and having allergies for a random sample of 40 students who completed a census at school survey. Here is a two-way table that summarizes the data. So you have allergies and no allergies as one of your variables, and the other variable is gender, and it is a random sample of 40 students. So we have um, 18 out of 40, which is 0.45. And then we have 22 out of 40, which is 0.55. Do the data provide convincing evidence of an association between gender and having allergies for U.S. high school students who filled out the survey? So, in the state portion, we want to perform a chi-squared test for association at a 0.05 significance level. Our null hypothesis would be there is no association between gender and allergies, and our alternative would be there is an association between gender and allergies. Checking the conditions, we have a simple random sample of 40 students. For the large sample, our expected proportion 0.45 times the total number of females will give us 10.35, which is greater than or equal to 5. And then 0.55 for no allergies times the total number of females. And we would expect 12.65, which is greater than or equal to 5. And do that for the males. So 0.45 times 17, that's 7.65, which is greater than or equal to 5. And then 0.55 times 17 is 9.35, and that is greater than or equal to 5. Okay, and for the independence condition, it is reasonable to assume that there are more than 400 students and the do portion. And again, you can definitely use the your calculator to help you get that large sample. The chi-squared statistic is equal to, and so we'll write out the first two. So observed for allergies, 10 minus expected is 10.35. Quantity squared divided by 10.35 plus 13, which is observed for no allergies, minus expected, which is 12.65. Quantity squared over 12.65 plus ... Anyways, I went ahead and found the chi-squared statistic to be 0.0506. Therefore, that's pretty alarmingly low chi-squared statistic. So the probability of getting the chi-squared greater than 0.0506 is lower bound 0.0506, upper bound, and our degrees of freedom. So we have 2 minus 1, and if you look at your rows and then columns, 2 minus 1. So that's a 1 by 1. So we have degrees of freedom equals 1. Right. And that gives us a p-value of 0.822. So since our p-value is not less than alpha, we fail to reject the null hypothesis. We do not have convincing evidence that there is an association between gender and allergies. And since we fail to reject, the follow-up is not necessary, not applicable. That makes us happy. Okay. Now, for the main idea for this chapter is which test should you use when. So this is a good little summary that kind of tells you when to use which. So the goodness of fit test you use when you have one variable and one population. So for instance, favorite color, and you're sampling everyone. It uses a one-way table to analyze the distribution of one variable. Or you can even do a breakdown of colors into different groups like blues, greens, reds, yellows, and so on. So maybe fave color and sampling everyone. Okay. For the chi-squared test for homogeneity, you have one variable, but multiple populations. So here, this uses a two-way table with the populations on one side and the measured variable on the other side. And so this one could be like fave color for Alaska kids and fave color for Texas kids. Couldn't think of any other state, so use Texas. Okay, and then for the chi-square test for association, that would be two variables, one population. Okay. So one sample basically. And this uses a two-way table as well, with one variable on one side, the other variable on the other side. So this could just asking one population, what state are you from and what's your favorite color? Right. The difference between test 2 and 3 is how the data is collected. Homogeneity uses two or more samples, then measures one variable, i.e., a sample of males, then another sample of females, then asks about their age. So the association independence uses one sample, then measures the two variables. So, i.e., samples people, then ask about their gender. So that's variable one, then ask about their age, variable two. Okay. Let's do one little example, kind of using that table of tests, and that'll help us do this last problem. So this is an article in the Arizona Daily Star from April 9th, 2009, and included the following table. So alongside the top, you have various age groups from 18 all the way to 65 and plus. And along the left side, you have whether they use online social networks or do not use online social networks. And here are some questions. Suppose that you decide to analyze this data using a chi-square test. However, without any additional information about how the data was collected, it isn't possible to know which chi-square test is appropriate. So, example A, explain how you know that a goodness of fit test is not appropriate for analyzing these data. So, hopefully, right away, when I mentioned that you had age alongside the top and then preference of whether social network preference along the other side, that you would know that this would not be appropriate for a goodness of fit test because, ah, okay. So, because there are either two variables or two or more populations, a goodness of fit, there we go, test is not appropriate. Goodness of fit tests are only appropriate only when analyzing the distribution of one variable in one population. One-way table. Right. B, describe how these data could have been collected so that a test for homogeneity is appropriate. So the test for homogeneity, if you look over here on the previous page uses 2 or more samples than measures one variable. So what you could do is we could take 6 independent random samples and each of those samples there'd be one from each age category. And then ask each person whether or not he or she uses online social networks. Because age can be the explanatory variable, and the response is using or not using social networks. Okay. And lastly, C, describe how these data could have been collected so that a test for association/independence is appropriate. So what you could do here is take one random sample and one, ask age, and two, ask whether, so these are 2 variables, or not they use online social networks. And that is it for chapter 11. Have a great day, AP Stat students.